Welcome to ODEs Lesson 25. Solution of the derivative with respect to t of the vector function x of t equals matrix A times x of t. And in this case, we're going to assume that the matrix A is diagonalizable. Let's suppose that the matrix A has n linearly independent column eigenvectors v sub 1, v sub 2 through v sub n, with corresponding eigenvalues lambda sub 1, lambda sub 2, lambda sub 3, all the way through lambda sub n. These eigenvalues are not necessarily all distinct. I'm assuming here that A is an n by n matrix. Let's construct the matrix P that looks like this. The first column of P is the eigenvector v1. The second column of P is the eigenvector v2, and so on all the way through v sub n. So this is going to be an n by n matrix. Then let's look at the matrix A times this matrix P that has the eigenvectors in it. A times P is the matrix whose first column is A times V1, the second column A times V2, all the way through the last column is A times Vn. But let's remember that V1 is an eigenvector with eigenvalue lambda sub 1. So this first column A times V1 is just lambda sub 1 times V1. Similarly, the second column is lambda sub 2 v2. All the way through the last column is the scalar lambda sub n times the vector v sub n. And if you look at this for a minute, you can easily compute that this matrix is just P times D, where D is the diagonal matrix with lambda sub 1, lambda sub 2, all the way through lambda sub n on the main diagonal, going from the top left to the bottom right of the matrix, with all of the entries off the diagonal being zeros. So we have that AP equals PD. If we multiply this equation on the left by P inverse, we will get that D equals P inverse AP. This is what we mean by diagonalizing a matrix. We were able to find a matrix P that we could use to diagonalize A by forming this product. P inverse A times P is diagonal. The P that does this, remember, is this special matrix up here whose columns are eigenvectors of A. This depends quite strongly on the matrix A having n linearly independent eigenvectors, where A is an n by n matrix. As an example, let's consider the following problem. Diagonalize the matrix A, which is this 3 by 3 matrix. We need to find the characteristic equation. The determinant of A minus lambda times the identity matrix equals 0. So first, let's evaluate the determinant of A minus lambda I. It's the determinant of this matrix, where we just subtract lambda from each of the terms on the principal or main diagonal of A. This is a 3 by 3 matrix. We can find its determinant by expanding using minors, expansion by minors. Let's use the first row. So we get minus 5 minus lambda times this determinant, this 2 by 2 matrix, which is right here, minus this minus 1 times the determinant of the matrix we get by crossing out the column and row that minus 1 is in. And so we're left with minus 2, 2, minus 1, 7 minus lambda, which is here. And then plus this entry times the submatrix minus 2, 6 minus lambda, minus 1, 1, which we have here. Then evaluate the determinants of these 2 by 2 submatrices. That's easy. It's the product of the terms on the main diagonal minus the product of the terms on the second diagonal. Simplify the polynomial that you get. It's a polynomial in the variable lambda. And then the characteristic equation, determinant of a minus lambda I equals 0, when factored, turns out to be minus these three factors equals 0. Product of these three factors equals 0. And so the eigenvalues of the matrix A are 4, 6, and 8. Those are the values of lambda that make this polynomial equal to 0 by having at least one of the factors equaling 0. To find the eigenvectors corresponding to eigenvalue lambda equals 4, we need to solve a minus 4i times that eigenvector equals the 0 vector. If we write this vector equation as a system of equations and then look at the augmented matrix, we have this augmented matrix for that system. Doing the subtractions that are indicated here, we can simplify that augmented matrix to this. 0, 0, 0, this extra column here, remember, comes from here, 0, 0, 0. If we look at the reduced row echelon form of this augmented matrix, we get this matrix. Now, if we look at this matrix, it has the same solution, the equations coming from it, the linear equations, the system of linear equations, has the same solution set as the system of linear equations coming from this augmented matrix. So this first row says that 1 times x1 minus 1 times x2 equals 0. There's no x sub 3 term. And so that's what we have here. The second row, 0x1 plus 0x2 plus 1x3 equals 0 is this. And then we see that from this system of equations, if we let x sub 2 equal the parameter s, then x1, x2, x sub 3 have to be s, s, and 0, which is the scalar s times the vector 1, 1, 0. So all of the eigenvectors corresponding to this characteristic equations are multiples of this one vector. Basically, the solution space is one-dimensional. So we can pick one of those, let s be 1. x1, x2, x3 being 1, 1, 0 is an eigenvector for the matrix A corresponding to the eigenvalue lambda equals 4. To find the eigenvector corresponding to eigenvalue 6, we have to solve a minus 6i times that eigenvector equals the 0 vector. So here's the augmented matrix for that system of equations, which simplifies to this when we do the subtractions indicated here. The reduced row echelon form of this matrix, this augmented matrix, is this one. So this corresponds to the system of equations x sub 1 minus x sub 3 equals 0 and x sub 2 equals 0, which we have here. That means that x1 and x sub 3, this entry and this entry, are equal. Let's call them s, parameter s, and x sub 2, this one had to be 0. So this vector can be written as s times 1, 0, 1. And so then we get x1, x2, x sub 3 is 1, 0, 1. Since all the solutions to this system were some constant times 1, 0, 1. So for lambda equals 8, we have to solve a minus 8 times the identity times the eigenvector corresponding to lambda equals 8 equals the 0 vector. So once again, as we did 2 times previously, we'll look at the augmented matrix for the system of equations, which is this one, perform the subtractions noted here, and so the augmented matrix can be written this way. If you look at the reduced row echelon form of this matrix, it turns out to be this. And so this is equivalent to the system of equations x1 equals 0, which we have here, x sub 2 minus x sub 3 equals 0, which is what we have here. And so let's see, x sub 1 has to be 0 from this first equation. The second equation forces x sub 2 and x sub 3 to be equal. Let's just call them both s's. And so we can write this vector as the scalar parameter s times 0, 1, 1. So x1, x2, x3 equals 0, 1, 1 is an eigenvector for lambda equals 8. Now we're ready to diagonalize the matrix A. We use the matrix P where these column vectors are eigenvectors of the matrix A, and then it turns out that P inverse AP is going to be diagonal with the eigenvalues on the main diagonal. We can check that this is true easily with a calculator or software such as Maple, Mathematica, SageMath, and other programs. This is what it means to diagonalize A. We find a matrix P such that P inverse AP is a diagonal matrix. The elements off the main diagonal are all zeros. The elements on the main diagonal can be anything. In this case, we have some positive numbers on the diagonal, the eigenvalues. Actually, 0 could be an eigenvalue of a certain matrix, so we actually could have zeros somewhere on this diagonal too. That's a possibility. So here's the problem we want to solve. Notice that this is in the form x prime equals a matrix A times the vector x. This matrix equation is equivalent to this system of equations down here. We can see that if we look at the first component on this side and the first component on this side, which is going to be this row times this column vector, we will get, just looking at the first components, x1 prime equals minus 5x1 minus 1 times x2 plus 1 times x3. Similarly, x2 prime is equal to this second row times this column vector, which gives us this equation. X sub 3 prime is equal to the third row of the matrix A times this column vector, which gives us this last equation. So here we have written quite explicitly a system of 3 first-order linear differential equations in the three functions x sub 1, x sub 2, and x sub 3, all of those being functions of t. We want to start with the system of equations x prime equals a matrix A times x, and we want to use diagonalization to change this into the form y prime equals a diagonal matrix times y. So let's see the details. If x prime equals the matrix A times x, x is a function, a vector function of time t, let's say. Then let's make this following substitution. Let's let y equal p inverse times x, where p is that matrix that we used in diagonalizing A earlier. Well, if we have this being true, differentiate both sides with respect to t, and we get that y prime equals p inverse times x prime. If we solve this for x prime by multiplying both sides of this equation by p, we get that x prime is py prime, and also x is equal to py. So let's see what happens when we make this substitution into this equation. X prime is py prime, so we have py prime here instead of x prime. On the other side, a times x turns into a times py, since x was py. So then multiply both sides of this equation on the left by p inverse. P inverse p times y prime is y prime. P inverse times this stuff is P inverse AP times y. But P inverse AP is a diagonal matrix, which we'll call D. So this equation is in the form y prime equals a diagonal matrix D times y. So let's consider the problem. Solve x prime equals a times x, where a is this matrix here. So basically, starting with that coefficient matrix, we saw that if we let P be this matrix, then P inverse AP was this diagonal matrix, which we can call D, for instance. And so we made the following substitution to diagonalize. Let's let y equal P inverse x, and then this equation up here is going to be y prime equals D times y. So we get this. We saw that before. And that gives us these three equations here. y1 prime equals 4y1. The solution to that is easy. y1 is a constant times e to the 4t. y2 prime equals 6y2 has solution y2 is a constant times e to the 6t. y3 prime equals 8y3 gives us the solution y sub 3 of t is c3 e to the 8t. Now, let's remember that we got here by letting y equal p inverse of x. So that's the same as having x equals p of y. So this was basically what got us off the ground in diagonalizing this system. So in that case, x, which is this, equals p, which is this, times y, which we just found out over here was this vector. And if you multiply these out, we get this. It's a column vector with this first component, second component, third component. Now if you look at this, we can break this into the sum of three terms. So x, x1, x2, x3 of t, is c1 times 110 e to the 4t. Where did that come from? Looking up here, we have a c1 e to the 4t. In this one, we have a c1 e to the 4t, and we have 0 e to the 4t down here. So we get 1 times this, 1 times this, stuff, and 0 times here. That's the vector 1, 1, 0 times C1 times e to the 4t. Collecting the e to the 6t terms from here, we can see that that can be written as C2 times 101 times e to the 6t plus C3 011 e to the 8t. Now, if we call this vector v1, we call this vector v2, and call this vector v3, we notice that v1, v2, and v3 were the eigenvalues of the matrix A. And I didn't say that right. v1, v2, v3 are the eigenvectors for this matrix A up here, corresponding to the three eigenvalues that we had, which were 4, 6, and 8. So we can see that x is an arbitrary constant times an eigenvector times e to the 4t, plus another arbitrary constant v2 times e to the 6t, plus c3 times another eigenvector e to the 8t, where v sub I is an eigenvector corresponding to the eigenvalue lambda sub I. Now let's look at this problem. Basically, x prime equals a times x, but this time we'll have some initial conditions also. x1 of 0 is 4, x sub 2 of 0 is 8, x sub 3 of 0 is 1. This problem can also be written in a non-vector and matrix form this way. We have these three differential equations, and down here we have the initial conditions. Let's see how we can use SageMath to help us solve the second problem. First, we'll define the matrix A. Remember, our equation was x prime equals a times x. Excuse me. So A is defined to be this matrix, and then we'll show A. So here's the matrix A. To find the eigenvectors of this matrix, we would use A dot eigenvectors underscore right, and then parentheses here. This will give us column vectors such that A times x is equal to lambda times x. The eigenvector will be a column vector to the right of A. SageMath also allows you to look at row vectors as eigenvectors by using eigenvectors underline left. But for our linear algebra type problems for eigenvectors, we'll use this. And here's the output. We're going to have for the eigenvalue 2 the following eigenvector, 1, 2/3, 2/3, and there's only one in the set of linearly independent eigenvectors for eigenvalue 2. Then for eigenvalue 3, we have this eigenvector, 1, 0, minus 1, a second eigenvector, which is linearly independent from this first one, 0, 1, 2, and here we have two linearly independent eigenvectors corresponding to eigenvalue 3. So let's see, any multiple of an eigenvector is still an eigenvector. So if we multiply this vector by 3, we can see that for lambda equals 2, an eigenvector for that is 3 times 2 times 2, 3 times each of these components. For the eigenvalue 3, we had these two eigenvectors, and we're thinking of those as column vectors because they're eigenvectors to the right of the square matrix A. And so our general solution to the ordinary differential equations, not quite the initial value problem solution yet, is that x equals c1 times this eigenvector for eigenvalue 3, eigenvalue 2 times e to the 2t plus another arbitrary constant times one of the eigenvectors for eigenvalue 3 times e to the 3t plus another arbitrary constant times another eigenvector corresponding to eigenvalue 3 times e to the 3t. So this general solution gives us all solutions to that system of ordinary differential equations that we started with. So far, we found the general solution to those three first-order linear differential equations. Now we want to specify that for the solutions to the initial value problem, we need x sub 1 of 0 to be 4, x sub 2 of 0 to be 8, x sub 3 of 0 to be 1. So let's plug in t equals 0 into here. And what we notice is that e to the 0 is 1, e to the 0 is 1, e to the 0 is 1 here. So we just get c1 times this times 1 plus c2 times this times 1 plus c3 times this vector times 1. c1 times this vector plus c2 times this vector plus c3 times this vector has to equal the 4, 8, 1 that we had here. Now, this is just a system of linear equations, and we've seen several ways of solving this sort of thing so far. We could make a 3 by 4 matrix where these 4 vectors are the columns, and then look at the reduced row echelon form of that matrix. If we do that, we'll find out that the solution to the initial value problem is, the solution to the system of equations is c1 equals minus 11, c sub 2 is 37, c sub 3 is 30. And so the solution to the initial value problem we get by just plugging in these values of the c's into this general solution up here. And so we get x is minus 11 times this vector, e to the 2t, plus 37 times this vector times e to the 3t, plus 30 times this vector, e to the 3t. If we wanted to, we could write a system of equations here for the solution. We could say that x sub 1 is minus 33 e to the 2t plus 37 e to the 3t plus 0 e to the 3t. X sub 2 is minus 22 e to the 2t plus 0 e to the 3t plus 30 e to the 3t, and x sub 3 of t is going to be minus 22 e to the 2t minus 37 e to the 3t plus 60 e to the 3t. We just saw that x is minus 11 times this vector, e to the 2t, plus 37 times this vector times e to the 3t, plus 30 times this vector, e to the 3t. We actually could combine these two terms into one, each with a common factor, that term having a factor of e to the 3t in it. But let's just leave it this way, since that's what we got as our solution. It could be simplified a little bit, I guess. Let's see how we can get the solution using SageMath, and then perhaps check to see if we have the same thing. So here in SageMath, we start by declaring t to be a variable, and here I put in something I'm actually not going to use. Also define c1, c2, and c3 as a variable. This was used in another part of SageMath, but not this calculation. We define x1 to be a function of t, x2 to be a function of t, x3 to be a function of t. We have 3 lines here defining the 3 ordinary differential equations. The first differential equation is the derivative of x1 with respect to t equals 0x1 plus 6x2 minus 3x3. This is the second differential equation. This is the third differential equation in our system. So then we're going to solve the initial value problem. So DE solve system, we're solving a system of differential equations. We have a list of the three differential equations here in square brackets. We're solving for x1, x2, and x3. Those were our functions of t up here. And the initial conditions are the following. At time t equals 0, x sub 1 will be 4, x sub 2 will be 8, x sub 3 will be 1. When we execute this cell by hitting Shift-Enter, this is the output. X sub 1 of t is 37 e to the 3t minus 33 e to the 2t. Let's check this one to see if it agrees with what we have up here. First of all, let's look at this and figure out what the e to the 3t term is. Well, we have here an e to the 3t also here. So what we get is 37 times 1 times e to the 3t plus 30 times 0 times e to the 3t, and that does add up to 37 e to the 3t. Now what about the e to the 2t term? Well, here we have minus 11 times 3 times e to the 2t, and that's minus 33 e to the 2t. We don't get an e to the 2t from either of these. So indeed, we do get minus 33 e to the 2 times t. You can check if you want to see that x sub 2 and x sub 3 here do agree with what we have up here. So we defined the functions x1, x2, x3. We defined the three differential equations, and then we used DE solve system with those three differential equations, solving for these functions and using these initial conditions. So what did we do in this lesson? We considered the equation x prime of t equals matrix A times x of t, or as our first example showed, y prime of t equals A times y of t. And if A is diagonalizable, in other words, if A is an n by n matrix, and if you have n linearly independent eigenvectors, we can diagonalize to get this in the form z prime of t equals a diagonal matrix times z of t. We saw that that's very easy to solve because it uncouples the equations. We just get each equation involving one function and its derivatives. And we can solve those as we solved before we talked about systems. So equivalently, we can instead find a set of linearly independent eigenvectors of A and immediately write down the general solution as a sum of terms of the form some arbitrary constant c sub k e to the lambda t times v, where c sub k is an arbitrary constant, lambda is an eigenvalue, and v is an eigenvector corresponding to that eigenvalue. I hope that you enjoyed this lesson and learned quite a bit, and please join me for the next one. I would like to thank you for watching this video. I hope you have found it to be an enjoyable learning experience. If you're interested in ordinary differential equations, there are additional videos in this series covering most of the topics in an introductory course in ODEs. Have a good day.